Looks good. Take it away when you're ready.
Okay. It's really nice to have a chance to talk here and really well organized. The talks are about optimal or whatever things about using ILP for eGraph. And here I'm going to describe how we use answer set programming on eGraph extraction. So I'm Ziyi, final year PhD student from Ilya's group. And after that, we are going to show some more outlook on how things working after that. So start with one single page. We want to extract the best expression or term in the eGraph because there are so many. Let's see, here are 3, and we are going to find the best. By default, is going to be the AST size. So the input of the problem is eGraph, and the definition, then the output is going to be the lowest cost term. So it has been known to be a NP-hard problem. And there have been attempts on using ILP, SAT, and greedy, whatever. So it's very hard, not just the previous slides, they are so simple, but in reality, the graph can be large, and there are loops, there are shared nodes, so overall it's a solver problem. Before going to the solver part, let me first introduce what is happening in the greedy part. So initially, if the node has no dependency, then we know the cost. That's the bottom stuff. And for the remaining thing, the cost of the node is going to be the cost of itself plus the children it is depending and what is being selected. So start from the bottom and trying to go up. So find that x is having the best cost because it's just 1 and the remaining are having 3. In a real case, the greedy search is about to find, in each E-class, find the best cost on its own without thinking about sharing. That is why DAG cost can sometimes be better than the greedy cost. Let's see, on the left, we are selecting the node of A in the E-class. The total cost is 29 compared to the thing on the right. It's actually selecting the node with cost 9, but it's optimal because there are shared node, and 5 is going to be reused twice. All right, that's the problem on sharing, and another problem is on cycles, because if the node you are selecting is having some dependency, you cannot do this because there's no way to extract the final term. Okay, so I guess I won't expect a lot of you know what is answer set programming. So we just introduced what's the problem setting. Now I'm going to give a brief background on what is answer set programming. So everyone should know SAT. SAT is basically find the propositional formula's satisfiability. Let's say we have by implication of A and B. Here in the CNF format is by something, and there's going to be 2 models. The first is both of them are false. The second is going to be both of them are true. And we also have Datalog. Datalog is logic programming way to encode certain reasoning. And we have A if B in the first line and B if A in the second line. The difference is the Datalog is having the least fixed point computation. So different from the classic implication, there's going to be only a single model which is empty. Basically, both A and B are being false. So you see the difference of implication and the logic rules here. So we're going to show a bit more later on how ASP is going to combine this together. But before that, one of the good things of logic programming is the things can be first ordered. Let's say we have basically here, initially we define some facts saying there's an A from A to B and B to A to B and B to C. And initially we also know A is reachable. Then we don't need to specify all of the rules to reason about which later nodes are being reachable. But instead, we have such first order rule saying, okay, if x is reached and there's an age, so we know y is going to be reached. So after this rules being grounded, is something like that. And finally, we know the model is going to reason that all of the nodes are reachable. And what I didn't say before is, in Datalog, by default, there's no negation in the body. And negation is really problematic thing in logic programming. Because if you think about the reasoning, you start from the body to the head. If the body are all of the positive literal, the model is going to be grow in a way. Instead of there's going to be negation to disable certain fixed point computation. That's why in the Datalog, there will be only one list model. But when we have the default negation, there's going to be choice between different models. Initially, we still have nothing in the model because we have A if not B and B if not A. But from the initial point, we can apply not B then A, and also not A then B. So there will be two models, and it's called stable model because after applying them, they are stable. No more thing can be applied. Yeah, that is basically the semantics, very basic semantics of the ASP, although in reality, there are a lot of different extensions from the basic logic programming path. So the high-level intuition about ASP is to generate different possible models and use the constraints, which in the form of rule without head, to eliminate certain models. And potentially, we have some optimization metric to get the optimal models. So it's like starting from things like that and encoding the constraints. And also, we have the max set style stuff. So basically, here we have the choice on A and B. And with eliminating the stable model saying, OK, A and B cannot be both true and both false. So we only have two in the end. Now we start to explore what is happening on ASP for extraction. OK, we are not the first one working on it. Actually, 3 years ago, our superstar Philip used to have a blog post on how to use ASP for eGraph extraction. And also, as we mentioned, Remy was also contributing to this. And the idea is to encode all of the eGraph facts into logic facts, and then use all of the ASP reasoning to dealing with the extraction. So on the right is the x plus 1 equivalent to y plus x, and it's going to be expressed by logic facts of in-nodes, child, and whatever. So that's 3 years ago. Still, bottom-up is the initial attempt on how to use ASP. Because the mindset is basically we are going to deal with loop. And if we have to eliminate the selection where there's a loop in it, it happened to logic programming happened to express the elimination of the circle. Because the first rule here is basically saying we can choose a node if all of the child have been selected. So if there's a loop, we will never reach this point because the semantics of the head and body is different from logical implication. That's really good insight, and Philip used to have all of this really clean implementation. And it's not working. I'm going to show a demo. This bottom up is the real code from, OK. So here's a eGraph page, 1,000 inode. If just use the default thing, it's going to cost, but it takes very long time. What I did after clone Philip's repository is just to see, OK, how about two-thread? And it's fast as hell. So what is happening right here is really about solver. Even if some expert know ASP a lot, it's hard to know what is happening in the solver. What really makes sense here is there's different optimization strategy. And if we are enabling something called unset core, it's just working. And it's not the default setting of ASP solver. And happens to be the case that the second thread is using that. That's why. So NSAT core is the game changer here. And the main difference is when we have the branch and bound, it's going to search the model in the whole search space and to bound the search. But the core guided search is going to try to have a potential cheap model and then do the NSAT core guided bounding on the max, on the optimization solving. And there's some historical reason because, okay, the NSAT part used to be implemented in EGRAPHS'. So by default, Klingo is still using the EGRAPHS' one, which is branch and bound. And that is working very well, but we also want to see what is happening to the top-down one, because the greedy is basically from all of the leaves and to the root. What's happening for the top-down is there's really issue about the loop, because you start from the top and you have to choose it no matter what that is, then it's never going to eliminate the circle. Fortunately, logic programming can express a cyclicity by transitive closure. So the transitive closure is basically having the reachability rule saying, okay, so something can be reachable and the recursion definition on it. But the problem of this method is about when we have the first order program of ASP, it's going to be grounded to propositional ASP. And it's going to be n to third for this. It's not going to be scalable for real EGRAPHS. So it's expensive grounding. What can we do here? It's called ASP model cyclicity. It's actually some kind of thing similar to SAT versus SMT. But when something is not easy to be expressed in logic programming, you just have the check outside the solving and have the propagator feedback to the ASP solver. And they happen to exist in the Klingo solver without any document. I just happen to find it. Okay, I try to implement it, and okay, I remember there's something, and it is working very well. So let's come to the evaluation part. So we have the expression gym suite, having 3 different suites, and 4 configuration. We have the bottom-up and top-down. Also, in the repository, the silver art is the optimized ILP. It's the naive ILP with a lot of pre-optimization or whatever. So our thing, as you can see, is really naive. It's just lines of code without some pre-processing or whatever. And we have 10-second timeout comparing with the 10-second result of greedy. So here's the quality. We overall find really nice number of optimal benchmark compared to not necessary to be the optimal, but better than greedy compared to the 10-second execution of greedy. And it's better than ILP in general on quality. And the performance is also quite impressive. As you can see, compared with faster ILP, we are still getting better on a lot of cases. And overall, we are much better than the naive ILP. And yeah, that is. And there's some real interesting case study when we try to explore what are the outliers, because as you can see, here the bottom-up one is having better optimal result, but overall it's slower. So here's my personal understanding on what's happening. So these 2 bottom outlier here are having a lot of roots on the EGRAPH. So if you think about how CDCL is working in SAT, it's also happening in ASP. When the root number is being small, starting from the root, you can get a lot of benefit by the CDCL loop. But if the root is containing a lot, starting from root is actually being costly because there are so many roots. But instead, starting from bottom can potentially prune a lot of root in that case. That's why, okay, that's basically my personal understanding on what bottom-up can be better in certain cases. And of course, this makes a lot of sense when you're trying to think about how the EGRAPH expression can work in general. There are so many solvers, And I personally believe that you need to understand what is happening in each property of the eGraph and to see what is going to be the correct solver or correct setting for different eGraphs. OK, here's a wrap-up of the ASP part. So ASP is powerful, but sometimes it powerfully sucks because the system is too complex. The language is hard to understand, and you need to understand what is solver working and also a lot of different settings. And that says we have quite good initial result on combining, on using ASP for eGraph extraction. What's going to happen next is we want to look at whether it's possible to combine them together, because we know that there's egg+log and ASP is essentially generalizing egg+log, generalizing data log with non-monotonic reasoning. So in the traditional egg+log, it's about we have the saturation, and then we compress by the saturation, and then do the extraction. How about that? We can possibly, OK, here are just about the brainstorm. There's no implementation yet, but I just want to share the idea. ASP is likely to be able to control the saturation. Instead of, you always do the fixed point computation. But the non-monotonous reasoning part of ASP is possible to prune something earlier, instead of you always do the saturation, reaching to the fixed point. And the high-level picture here is, OK, we use ASP for defining the search and the efficient search in the CDCL style stuff. And eGraph is essentially compressing the search space. And hopefully there's something happening to, just like what is the previous talk are talking about. There are different ways to do the search, and hopefully ASP can come here to do something. And I want to introduce a bit more on what detail the ASP's features can contribute here. The first is called incremental solving. So incremental solving has been applied a lot in stat solving. Basically, you know the whole search space, but you don't want to search it at once. But instead, you are having some initial result on a subset of the constraint solving. Then after that, you are going to make the search larger by introducing more literal or whatever. And that is quite similar to what is happening in equality saturation, because it's step by step, we keep applying the rules and finally reach something. And the second thing is really about the propagator I mentioned a little bit. Is somehow complex, but the reason I'm mentioning here is I don't think equivalence is very straightforward to be expressed in logic programming. But if there will be a good customized propagator that we can do ASP modulo equivalence, that is potentially the way to combine the things together. And both of them are likely to benefit from each other. OK, here's the overall takeaway. I personally think that even if the performance is promising, it's still small lessons, because extraction is overall just problem never going to be solved very well because it's NP-hard. But yeah, we have all of the techniques in ASP, and potentially if we are applying all of this into equality saturation, we want to benefit both of them. OK, so closing. If you are willing to try more on ASP, you can try Klingo, which is a state-of-the-art system having a lot of interesting features. And if you find it too hard to use, I'm here open for any collaboration on ASP. And we also have designed a new front-end language for ASP, which is going to be released soon, hopefully to improve the user experience of ASP. OK, that is. Thank you.
Thanks for the talk. We definitely have time for questions. I'll start off with a question. So I'm by no means an ASP expert, but it seems like you were sort of hinting that there's these internal notions of propagators and this graph propagator, and then at some later point you have this ASP plus egg slide where ASP is sort of handling the choice element. Are you sort of picturing congruence closure and, well, maybe what else as a sort of additional propagator, or maybe say a little bit more about how you might split split up those two things?
Yes, so it's really interesting, and also what I'm thinking of, because in egg+Datalog, things are just like fixed point computation, but we have choice here, and potentially if everything in the egg+Datalog can at least be encoded in ASP, and we extend all of the thing to ASP part, I guess the propagator is likely to be the way, because I don't think, in principle, there are better way to extend the basic logic programming method. The propagator in practice is not that straightforward to discover, because you need to find what is the feedback one from the theory. But yeah, for the age, for the cyclicity, it's pretty good.
Okay, so maybe I missed it, but you mentioned faster ILP and ILP, or what's exactly the difference?
So the faster ILP, so the ILP is basically encoding the constraint solving in a file and run it in CBC. And faster is having some pre-processing. Okay, I didn't read every code of that, but I find certain judgment on if there's some node with zero codes, then some elimination or some optimization based on such information. So my personal understanding is, okay, get some very specific optimization and make the overall things faster. I'm not an expert on the ILP part.
I have one more quick question. One of the things that is interesting about the language we use, not only in equality saturation, but compilers and stochastic search, is we say optimization, but really we mean sort of embedderization. Like, we're okay with making things better, and in many cases it is not wrong at all to return a non-optimal result.
Sure.
And we saw this in some of the previous talks about how if the ILP solver is running in a mode where it can give back a non-optimal answer, things can be much faster. So I guess my question is, what does ASP offer in that regard? Like, can I move towards a potentially better but not known to be optimal solution, and can I use that to make scalability much better?
Yeah, actually I have never think about it, but there are heuristic-based programming in ASP. So I suspect that the heuristic is basically similar to sassoing, but if you have some domain-specific things for the certain class of EGRAPHs, you can always encode them to guide to the solver reaching to suboptimal stuff in a way, collaborating with CDCL. I mean, there's no theoretical result, but there's something in the existing solver.
Okay, cool. Thank you very much. And with that, let's thank the speaker one more time.